All right, ladies and gentlemen, welcome to our talk. It is my pleasure to introduce to you Edwin Brady. Now, I want to see how much you know about Edwin Brady. He is a lecturer at St. Andrews, I see. They're very enthusiastic. It's a very enthusiastic, I see. Famous for a dependent type system called Whitespace, indeed. That you're ahead of the curve. He's also famous for Whitespace. And Idris is called complete. No. Tetris complete. Very good. Why is it called Tetris complete?
Well, we'll come to that.
Oh, well, there we go.
I actually call it Pac-Man complete, but I think they're equivalent. There's probably a theorem.
Do you have proof?
No, I've got a constructive proof of a step on the way, but we'll see that.
And his favorite beer is Budweiser, correct? Right?
Arrest that man.
All right. Ladies and gentlemen, please, a warm applause for Edwin.
That's my name, yes.
Yeah, there we go.
Okay, so thank you very much for that introduction. Also, thank you very much to John for inviting me. It's, I don't quite know why he invited me, because to be honest, I don't actually know any Scala. My link to Scala is a little bit tenuous. Some of you might have seen a couple of years ago, I gave a talk with Miles comparing Scala to Idris. And that's kind of my link. So my experience of Scala is playing around with shapeless, which is kind of like running before you can walk. So I've been letting these talks kind of wash over me, trying to get the ideas rather than thinking too much about the syntax. And I've picked up a lot of very interesting ideas from the talks that I've seen, and I hope that you'll pick some in return. And the most important thing is, even if I'm not really here to convert you from being Scala programmers to being Idris programmers, I'm really here because I want you to steal my ideas. So if you can pick up some ideas that you see in Idris that you think you can apply to your Scala programs or more widely, then please do. Just to say another thing about that talk with Miles. What actually happened? He is here. So what we did was I wrote a couple of Idris programs, and they were basically challenges for Miles. I wrote programs using the full dependent type system in Idris and said, okay, Miles, can you do that? And to my amazement, I shouldn't have been amazed, but to my amazement, he did. So this talk is going to be the next step in that game. So we'll see what happens.
Challenge accepted.
Excellent. Challenge accepted, said Miles, if the video didn't get that. So internet, Miles said challenge accepted. Right, so a few people have asked over the last couple of days where I'm from. I'm from St. Andrews, and St. Andrews is in Scotland. And one thing that you may or may not know about Scotland is that it is in some sense the spiritual home of functional programming, in that Haskell arose from Scotland, ML, it was a Scottish programming language, and we now fly the flag in Scotland to reflect this important bit of the nation's history. So it seems only right that I should present another Scottish functional programming language. Okay, so I'm going to talk about Idris. It's a Pac-Man complete functional programming language, and by Pac-Man complete, I basically mean that there is enough available there that if you wanted to, you could implement Pac-Man. So people talk about, if a new language appears, people think, people ask, is it Turing complete? They might worry if it's not quite Turing complete, but I think that's not really that useful a thing to say about something. Whitespace, for example, is Turing complete, but it's not Pac-Man complete. Again, maybe someone will accept that as a challenge to prove that. But I think it's far more useful to say something is Pac-Man complete, simply because if you have the ability to take your fancy language and talk to system libraries and do system interaction, then you have something that is, potentially truly useful. I also have, right at the beginning, the instructions on how to install the thing. If you have the Haskell platform installed, I don't know if a room like this is likely to have the Haskell platform installed. Maybe they've shouted at it a few times. But there are binaries available that you can go and download. And all of the examples I'm going to present in this talk, all of them are available online for you to play with and just try out for yourself. So there's going to be two parts. I'm not going to assume that anyone knows anything about Idris. I know that a few people might have tried. Actually, just for my own, vanity, I suppose. Do we have a show of hands on anyone who's given it a go? Oh, actually, that's quite surprising. Thank you. So I'm going to say a little bit about the syntax and just some of the basic ideas of it. And hopefully, even if you have seen it before, there will be something new that you'll pick up. But what I want to get to is why I think first-class dependent types, so having dependent types in the language right from the start and built into the language as an intentional feature is a truly valuable thing to have. Hopefully you'll start, when you're writing your fancy Scala programs with your type level extensions, you'll at least be thinking, okay, how might this work if I was able to express it with first class types and maybe get a better understanding of what's going on underneath. So the examples I want to show you are the sort of things that, the sort of places where I think verification has a good chance of being useful in the short term. So realistically, we're not going to be able to say in the near future, I've written the program, it type checks, ship it, it's okay. But we are going to be able to, there are going to be fragments of our program, say when we're working on network infrastructure or the core components of our programs that we really have to be confident, like we're writing avionics software, we want to be fairly sure that it's doing the right thing. So those core components, I think in the near future we have a reasonable chance of being able to use these kinds of dependent type techniques to work in those spaces. I'm going to give you some idea of how we might be able to do that using a language like Idris. So I want to say a little bit about what I see types as being useful for. So I've titled this talk Type-Driven Development in Idris for two reasons. I'll come to the second reason later on. The first reason is that I've seen a lot of types over the last day or so, and a lot of people have said types are for giving us confidence that the program is correct. If the program type checks, we know that it's going to work to a certain level of work. And that's great. That is absolutely true. The thing is, there's so much more you can do with types. We should be using types not so much as a way of having the machine tell us when we've done something right. We should also be using types as a means of guiding us towards the program that's going to work. So it's too easy to think of, you write your long program, you submit it to the type checker, you send it to your teacher for grading, and it comes back and says, 3 type errors, see me after class. What we want to be doing instead is thinking of the type checker as your lab assistant. So if you write the type first and say, okay, lab assistant, this is what we're going to do, let's work on it together. Every so often you might be able to say, okay, I'm not sure how this program works, can you give me a clue? Rather than generate some code and test because it looks like it might be right and see if the type checker accepts it. So we'll see some examples of how that goes as we get onto the examples shortly. And the sort of mantra that I've started using that we're going to see throughout is like test-driven development has red-green refactor. We have type, define, refine. I'm very sad that I couldn't find a word for type that rhymes with define and refine, by the way. So if anybody has one, let me know. So everything we do is going to be either write or inspect a type, define a function, and we can define functions that are possibly incomplete. We can say, okay, we have most of a function, and I'm going to leave a hole for the bit of the function I haven't written yet. And then another thing we can do is refine. So I'm going to use the word refine a lot. We're going to take a definition that's possibly incomplete and refine it so it either has a more complete definition or a slightly more informative type. And basically everything we do comes into one of these 3 headings. So every time, all the time, think, is it a type? Are we defining? Are we refining? And I suppose we can add refactor at the end. Once we have a working program, we can safely refactor, knowing that if it continues to type check, it continues to be okay. So just before I get onto the demo, I want to do a quick rundown of some of the features Idris has, because it's kind of an FAQ that people always ask me. Firstly, first-class dependent types. So I say first-class here, meaning that the syntax and semantics at the type level and the value level are the same. So there's no difference, there's no sort of barrier, there's no barrier between the two languages. It really is completely the same language. Anything you can write in an expression, you can write in a type, and vice versa, as long as it type checks. So when you introduce functional programming to people, we often say that functions are first class because it means we can pass them around just like any other value, we can compute them just like any other value. Well, in the first class type system, same goes for types. We can compute them, build them, just like any other value. It does have a Haskell-inspired syntax. I sometimes regret that because it means people think Idris should work like Haskell. There's various ways in which it doesn't. I just happen to like Haskell syntax. There's a few things that have changed a little bit that I didn't like too much, like single colon for types instead of a double colon, that kind of thing. It's a compiled language. There are two code generators that you get when you install it. One via C, just for writing native code. One via JavaScript. It does have a pluggable backend system, so you can plug in if you have it's exporting an interface to the intermediate language. So if you want a JVM backend, then by all means go ahead and write it. I'm happy to help. Having precise types means that we get optimizations too, so we can really do aggressive inlining, aggressive erasure. It seems to me that if the compiler knows more about the program, what the program's supposed to do, it should be able to do more work at compile time to make that program more efficient. So things like removing dynamic tests that are unnecessary and so on. Has type classes. I bravely put like traits in Scala, hoping that was correct. Is that correct? Sort of, yeah, all right. It has type classes. It's essentially a way of defining interfaces to a type. Interfaces that say what a type is able to do. Unlike Haskell, strict evaluation, but if you want lazy evaluation, you can have laziness as a type. We won't actually get to that in this talk. I'm just saying that because somebody always asks. So strict evaluation. And there's various bits and pieces to do, foreign functions, system interaction. Okay, so mostly what I'm going to do, though, is a bit of live hacking, because it's more fun if I actually show you things happening. And it's also more fun if instead of me just doing stuff, you shout out questions of the form, what if you do this, that, or the other, just to prove that I haven't made this up. If you want to shout out suggestions and take this in a different direction. Okay, so what's the answer to this question? Yes, good. Let's move on to something else then. I guess actually I could just to show you things compiling and running, because I don't know how familiar you are with the sort of theoretical end of dependent types, but sometimes there are genuinely people who think it type checks, I don't need to bother testing it because I already know it works. And to some extent that's true, but we do actually want to ship these and sell these at some point. So if I can sell you my Hello World program, I can compile it to an executable, and there we go. So it's we have a batch compiler that works in the usual way. We also have a read eval print loop. So again, all the tools that I guess you're familiar with from other languages. So the first example I want to show you is the simplest first-class type. So if you don't get what I mean by first-class types, this will hopefully make it more clear to you where the distinction really is between types and values. There isn't one. So I'm going to start by writing a function that takes this is in the Atom text editor, by the way. So I've started using the Atom text editor because I've been using Vim for talks, and people say to me afterwards, that's very nice, but I wish I didn't have to use Vim. So I'm using Atom just to prove that you don't have to use Vim. I will probably get my fingers in a tangle at some point. When we do type-driven development, it's always types first. So what I've got in this file is a couple of types, and we're going to use the types to lead us to a program. So type first. This type here is going to be the type we calculate is going to be if the Boolean is true, we're going to have it return. So the Boolean means singleton. If it's true, we're going to return a singleton natural number, and if it's false, not a singleton, we're going to return list of natural numbers. So what I do in Atom is I say, okay, I've got the type, give me a skeleton definition. So this is Control-Alt-A for add definition, and it gives me a skeleton definition. So this thing here, list type RHS, this is a hole. So this is syntactically valid. I can load this into, in fact I will load this into the intro 0 So I can load this into the REPL, and it will happily load it, and it will say, okay, you've got a couple of holes. Is that color legible? It's not really, is it? I'll turn the color off. There is a U in color, by the way. Thank you. I didn't expect that. Right, so So we can also inspect the type of this hole inside inside Atom. So Control-Alt-T down the bottom here, it will give us an interaction window that tells us, well, the result of the thing we just asked. There's a few other things we can do here, like we can ask for documentation. So if I hover over NAT and hit Control-Alt-D, it'll give us the documentation for NAT and tell us what the constructors are. So there's various useful bits and pieces that allow us to interact with the system. This is all, Idris is doing all the work here, by the way. This Atom is has a very thin wrapper, and this means that you can easily adapt this to your favorite text editor. And there are Vim and Emacs modes. Okay, so we can also inspect. Well, we write programs by inspecting the possible values for input. So singleton, the possible values for singleton here, since it's a bool, in fact we can have a look at what they are. The possible values are false and true. So if I hit Control-Alt-C for case split over singleton, it will split that into the two possibilities. And if you remember, I said before, if it's false, not a singleton, it's going to be a list of NAT. And if it's true, it is a singleton, it's a NAT. So why would we do this? Why would we write functions that calculate types? Well, it's if we want to use them in types. So something we can do is let the types of later inputs be calculated from the types of earlier inputs. So we're going to run this function, because this function returns a type, we're going to run it in a context where a type is needed. So sum list here, this is going to sum either a list of things or give the value of a natural number depending on the value of singleton and the next input. So if I look at the type of this whole, we'll see that the inputs we have are singleton, which is a Boolean, and X, which is a list type calculated from the value of that singleton. So I can't really make any progress here, or the only interesting thing I can do, the only thing I have available, is to inspect singleton. I can't inspect X yet, because I don't know what type it is. I don't know what type it is until I've run this function. So I'll do a case split on singleton, and if I now inspect, so I'm going to look at the type of sumList RHS1, so that's one of the holes that's been created. We know that singleton is false. X has type list type singleton, so if I look at the type of this now, you'll see that it's refined the type of X. Given that it now knows that in this context singleton is false, X must be a list of NAT. And correspondingly, if I do a case split, it will give me the cases for list, and in this other case, if I do a case split, it'll give me the cases for NAT. So what's happening here is from the type or the value of one input, the machine has worked out the value of the next input. So I'm not going to complete this definition, but I'm going to show you a definition where this sort of thing happens in, for example, C. If you've ever done any C programming, you've used exactly this trick when you used printf. So I have also in this file, I'll show you the type of printf. So the type of printf, this is exactly the same trick we've just seen. So it takes a format string as an input, and the return type is calculated from this format string. So if I do the type of printf%s, it'll say, okay, that's a string to string, or %s%d, okay, that's a string to int to string. And so C compilers have to do this through some compiler hacks to make sure you've got the right format of string. This is just done in pure Idris. So this is the kind of thing you might use first-class types for, is if you have maybe some schema description, and that schema description will calculate the valid types of your database queries, for example. So it's just scaling this up. Okay, so that's Hello World example 1. Hello World example 2 is going to be vectors, because it's always vectors. And some groans, I can hear some groans. The reason we use vectors, so vectors are lists parameterized by their length. The reason we use vectors as a Hello World example is because unlike printf, they're genuinely useful. So I'm always writing programs, certainly in Haskell, where I make the assumption that a list I have is non-empty, and that assumption is completely valid for the program I've just written. And then 12 months later, I violate that assumption in some other file, and I get a crash that was unexpected. So this is the kind of thing that I would love to have available, straightforwardly when I write my Haskell programs. So what happens with a vector is you declare types basically by giving a type constructor that says how to build that type, and some data constructors say how to build the values in that type. So nil here is a vector with 0 things, and cons is a vector which, given a thing and k things, k more things, will have successor of k things. So successor of k, s of k, you can read that as 1 plus k, basically. So nat is a data type defined with constructors 0 and 1 plus the nat. The sort of thing you can do once you have that is well, you can express invariants on the functions you have over lists. So if I have a function that I want to apply a function to two corresponding vectors. So this is the zip width function that do you have any? You presume you must have an equivalent in Scala. You've got everything in Scala. Is it called zip width?
Yes.
Yes, good. So this is taking two corresponding lists, and there is a question of what do you do if the lists are different lengths. So there's some perfectly reasonable things you could do here, but quite often, I don't know about you, certainly when I use this, I make the assumption that the lists really are the same length, and if they're not, I should be doing, I should do something about that beforehand. So here I've expressed in the type that the two vectors that are coming in are the same length, and the vector that's going out is the same length. And the wonderful thing about type-driven development is that given that I've put a precise enough type for that function, the machine can tell me how this function is going to be, or give me some hints about how this function is going to be written. So what I'll do first is I'll make the skeleton definition. So this is Control-Alt-A, as we did before. I could do a case split on the possible inputs. So I'll do a case split on x's here. And if I look at the type of zip with RHS2, we'll see that y's, so we've got x's with an empty vector, and y's must be a vector with 0 things in it, because x was. So it's the only thing y's can be. So if I do a case split, it will only give me the one possibility. It won't even suggest that I have to deal with the non-empty vector, because it won't type check. And the fun thing about this is, so if I look at the type of the right-hand side now, you'll see I'm looking for a vector of 0 things. It's kind of fun that I can just say to the machine, OK, just search for a possible solution. And well, it's dead easy in this case. There's only one empty vector, and that's the empty vector. So I'll do a similar thing here. I'm not going to bother thinking. I'm just going to hit case split and expression search. And well, I think that's the only reasonable answer, to be honest. So hey, the machine did the work. The machine thanks you. This doesn't, by the way, this doesn't free you from knowing what you're doing. It's kind of important to look at the result of that function and see that it's produced the answer that you think is the answer. Because a lot of the sorts of things I use this for in practice, this kind of expression search, is for tricky monadic plumbing. Or where you have some type f of a and some type g of b, and you've got various ways of getting from a to b, but you can't figure out how to do it. Normally I start by expression search and see if the machine can figure it out. And often it can figure out some of it, but not all of it, and that's already a big help. So this is, I'll do another example of vectors. I think this one's quite fun, because it really does demonstrate the kind of, so if I'm going to try to transpose a 2D list, basically. And trying to transpose a two-dimensional linked list without the help of types, I think is quite tricky. It's the sort of problem I set to my data structures and algorithms class. I give them a two-dimensional linked list and make them transpose it, and they hate me for the rest of their university career. And I don't really blame them, especially given that we teach in Java. There, I said it. That's the sort of thing I shouldn't say on a talk that's videoed for the internet, is it? I'm going to be in trouble now. I read it. OK, so transpose vec, we're going to do the same thing. So we've got an n by m vector, and we want to give back an n by n vector. So this x's is a vector of stuff. I mean, the only reasonable thing I can do at this point, the only thing I have is x's. So I'll do a case split on it. And in the first case, so if x is an empty vector of, so if the input was an empty vector of stuff, I have to transpose to a vector of empty vectors. So I can look at the type just to see what the type thinks I should do. It says I need to produce a vector of m empty vectors. Now I can't be bothered to do that immediately. I'm gonna call it empties. I'm going to say, right, I'm going to rename this hole to empties and hit Control-Alt-L. And what that does is it lifts a new top-level function with the type I need to fill in that gap. And I'm going to come to this later. I'm going to move on to the interesting case. So in the interesting case, what have I got? So step is, it's always, type, define, refine, write the type, do some definition, look at any more types, refine the definition. So I've done a type and a define step. I've done a bit of refinement here. So let's look at the type again. So don't make any progress until you've seen the types that you need to be working with. So let's look at the type of transpose vector RHS2. So I have a vector of m things. That's our x. So this is the first row. So in fact, I could even rename it, because I gave a talk a while back, and someone afterwards came up to me and said, "It was a very nice talk, but why do you functional programmers always call things x?" That's a very good question. But here it's clearly a row. It's a row of things, so let's call it row. And we have a vector of k by vector of m things. So it's going to be much more useful, given that row is a vector of m things, and I need to produce a vector of m things. It would be much more helpful if x's was also a vector of m things. Now we know how to turn a k by m thing into an m by k thing. We make a recursive call. So what I'm going to do is exactly that. And then ask the same question. Ask the question again. So the type now is, so there we are. I have a vector of m things, another vector of m things, and I need to make a vector of m things. That's exactly what we did in zip with, actually, isn't it? We took two vectors of m things, and we made a vector of m things. And I don't really want to worry about filling in the details here, so I'm just going to lift that up to a top-level function. So I'm going to write a helper function, and it's given me the type, which is nice of it. So it's filled in the call to this function I'm about to write, and now it's given me a type, and I can do the usual thing of skeleton definition, k-split, refine. I happen to know that I'm not going to need x's, so I'm going to delete it. And let's just, well, you might be able to guess what I'm going to do here. It's kind of easy because I've done this before, but I happen to know that all I have to do is k-split, search, k-split, search. And that's our helper. And similarly for empties. So you'll notice here that there's an m in there's a type variable m, and that's awkward because I want to use m, and m's in the type. But hang on, types are first class, so why don't I just bring it into scope? So since types are first class, I can just bring this value from the type into the program, and again, k-split on it, and this is just going to recursively build an appropriately length list of empty vectors. So you may not have followed exactly what was going on in the program there, mostly because the machine was just doing the thinking for us. But if you look at the types here, you can see exactly what's going on. From the top here, you can see that if we can only be making a transpose vector here. I mean, we could, if we tried quite hard, we could make a transpose vector containing the wrong things. Except we couldn't, because we haven't said anything about LM. LM is just a type. We know nothing about it except that it's a thing. So I guess we could be reversing things or making a mess of the structure at the same time. But really, the only natural thing we're going to be doing here is transposing. Again, if you look at the types here, you'll see that we have a row, which is a vector of m things. We have a transpose thing, which is a vector of m things. And you can sort of, if you squint a bit at the types, you can see, well, I've got an m, I've got a thing, and I've got k things, and I need to make successor of k things. So essentially, I'm just gluing the row onto the front of the vector. Okay, so I should test that, shouldn't I? Because, it type checked, so we know it's going to work. But I've created a main program that takes some dimensions of a vector, invents a vector, and then transposes it for us. And so, what did I call it? Intro to. Actually, why don't we use a different code generator? What could possibly go wrong? Oh, compiled. So 4 rows and 3 columns. So that's a vector of sort of 3 columns, 0, 1, 2, 3, 4, 5, and so on, and it's transposed. And we believe that's transposed. And just to prove that that really was a PHP program doing that, there you are, a bit of enterprise-ready PHP. So if you ever need, this is I actually wrote that PHP backend for a bet, but you know, almost genuinely, if you happen to be writing a WordPress plugin, as I'm sure you do every day, and you want to have some kind of confidence that there is some functional correctness to your WordPress plugin, would you rather write it in PHP or in a functional language? I don't know. Well, I do know. I'd rather write it in a functional language. Okay, so so much for the introductory stuff. How am I doing for time? 10 minutes? Where's mine? 10 minutes, okay. So that's a couple of Hello World examples. What I want to show you to finish off is something a little bit more, I think, realistic of the sort of things you might want to do, is writing down state machines or state transition systems and making sure that you're properly following the appropriate state transition. So this is the simplest one I could think of that demonstrates the point. It's the door open and close state machine. A door can either be in the open state or the closed state. So we'll start in the closed state. If the door's closed, we're allowed to knock on it, but that doesn't change the state. And if the door's closed, we're allowed to open it, and that changes the door state to open. This particular door, you're not allowed to knock on it if it's open. So this is a sliding door, so the door vanishes. And if the door's open, you're allowed to close it. So this is this might seem a slightly familiar kind of API. I mean, like file handling takes this kind of form. So you open a file. There's certain things that you can do to a file when it's open. There's certain things you can do to a file when it's closed, and they're not necessarily the same. And it would be nice if in your API you could properly express this kind of property of when you're allowed to do certain actions and what those actions do to the state. If you can characterize the state of your system in some abstract way, then you have some hope of reasoning that it's doing the right thing. So I'm not going to go through the details of how this works exactly in Idris. I'm just going to show you the types, and hopefully the types will be clear enough that you'll believe that they really are expressing this door system. And for this, I'm going to switch back to Vim, just to show that you can have multiple editors. Also because we're going to see error messages, and I haven't figured out how to get the error message font bigger in Atom yet. That's one nice thing about this type-driven approach, by the way. You generally don't get a lot of error messages because the machine is only giving you correct programs. And when you do get error messages, you know exactly where the error is because it's in the tiny bit that you just wrote. So I find it very useful, even when I do get error messages. Rather than try to figure out what's going on by staring at the program, I tend to pull bits out of the program and replace them with holes and see if it starts working again. I find that a really helpful way to use types to get me to the right program. Okay, so this is a representation of the door state machine using, it's a library called effects. It's distributed with Idris. And F here, I'm going to describe F as a kind of domain-specific language for building your own monad. F is actually a monad. It's a library that allows you to compose different bits of stateful system, different bits of effects in your system without having to worry about the plumbing of monad transformers. It also allows you to change the set of effects that you have available as the system progresses. So here we've said in the type of open door that it's an effectful program. It returns unit. It starts with a door in the closed state and it ends with a door in the open state. And closed door is the other way around. And then knock here says you can only run it if the door's in the closed state and it doesn't change the state. So this door program here is a type correct, therefore resource correct use of that door protocol. So if I do something like knock and then close the door, so basically what I'm trying to do here is close the door when it's in the already in the closed state, and it says it went wrong. This bit here says it went wrong, and this bit down here is the thing that tells us something useful. So there is a mismatch between the door it should have been open and it was actually closed. If I try to open it twice, this is a slightly more readable error message. We have a way. The error messages are sometimes a bit more helpful depending on if the system recognizes the structure of what's going on. So here it says, you did something that required the door to be closed, and actually the door was open. So you can only open the door when it's closed. So Now it type checks again because I'm following the protocol properly. So what sorts of thing, I mean, this is great that we can follow the state machine, but the problem here is we have specified what those state transitions were, and we don't always have control over the world. For example, the door might jam. There might be a problem with the door. It might need oiling or something. So the door might jam. So I don't necessarily know when I open the door if I'm in an open door state. So comparing with files, you don't necessarily know if you open a file if you're going to have an open file after you've done that. You might have an error. So we really need to find some kind of way of expressing that in the type system in order to have some reasonable claim of safety. So fortunately, having first-class types means that the things we put in the types to say how the state transitions work, they're just programs. So this is the bit that I would love to see Miles do. So now my open door type says, okay, I've started in the closed door state, and instead of moving on to the open state, I'm going to return the jam status of the door. And it's a function from this jammed is of type jam, and I will inspect that in the type, and if it comes back with jammed, then the door is closed. If it comes back with OK, then the door is open. So down here I have a valid. If I try the thing like before, it's going to say, no, sorry, you can't do that. That's actually a slightly worse error message than I was expecting. But the point, the things to look at is we have a door that's open, and it's we need to have a door that's open, and we have a door that isn't when we close it. So instead, what we'll do is we'll take the return value of opening the door. I'll stick a hole in here for the rest of the program, and if we look at the type of that hole, so Vim has all the interactive editing gadgets too, so I do \t to get the type. So I have this OK of type jam, and you'll see that OK appears in the type. So this is a hint that to make some progress here, if we inspect the result of OK, with any luck, this type is going to refine to something useful that we can work with. So let's do that. So I don't like writing case blocks. I write them, so Idris writes them for me. So we'll inspect OK. I'll do a case split on the result of I'll do a case split on the result of OK. So in the case where the door is jammed, then.
Sorry, just a question on the case splitting. When
Yeah.
you do that, are you calling out the Idris
Yeah.
compiler? Or?
Idris is doing all of the work here, which is good news for editor plugin writers, because you don't really want when you're writing an IDE, you don't really want to have to be re-implementing the entire type system again, especially if the type system is evaluated too. So yeah, what's happened here is that in this branch we know, because the case analysis went through the jammed case, we know that we have to calculate the state where the door is jammed. So the door's closed, and we need to be in a door closed state. By the way, you'll notice that I put std.io here as well. So when we have effectful programs, we can list the effects that are available. So it means I can do something like, some kind of cartoon struggle noise, and then have another crack at it, and that'll be okay. So in the OK case, if we look at the type here, we'll see that we're in the door open state. We need to get to the door closed state. So there's no way this program is going to type check unless we actually close the door behind us. So we were not born in a field, so we'll close the door behind us, and that type checks. So now this is a valid use, a correct use of the door protocol under the possible situation of the door not closing properly. Just one more thing before my final quick bit of code, quick example that I want to show you, is that this kind of thing where you're testing for errors and dealing with an error case and dealing with a success case, you could imagine some very deeply nested code if this gets longer, and you might think, oh, can you throw an exception and have a handler? So what I did instead is I decided to borrow a feature from Perl. I love saying that because for the reaction. So So you know the open file or die syntax in Perl? Any Perl programmers?
Yeah.
Yeah, you know that syntax. So this is kind of the same idea, that you have a main path that you work through, and then this alternative this is only called in the event that open door doesn't match OK. So I can quite happily have a load of opening and closing the door, and that's fine. Right. So why would you do this sort of thing? Sort of reason you might do this is if you have a system where there are rules, and those rules change, so some complicated rule system where the current state dictates the kind of things you're allowed to do. Like, for example, the game of Hangman. So the game of Hangman, the state is reasonably simple in Hangman. So this is I tried explaining the rules of Hangman and the backstory behind Hangman in some documentation, and I couldn't do it. I had to call it mystery word because it was just sounding far too gory. So the idea is you're guessing letters, and if you're guessing letters in a word, and if you guess correctly, you basically want to get down to no letters still to guess, and you don't want to get down to no guesses available. So I have captured the possible states of the Hangman game by saying, okay, a game is either running with some guesses and some letters, or it's not running. So this is kind of like our door open, door closed. We've got two different states. It's just that one of the states has a bit more information in it. So let's not worry too much about the exact details of how that's represented. But the important point of this, the important function in this system is if we guess a letter, that letter is either going to be in the word or not in the word, and that's going to change the state of the game depending on whether we were right or not. So guessing a character is an effectful program that returns true or false. It can only work if we have some guesses available. It can only work if we have things still to guess, and it will either come back with guess still available and a letter gone, or a guess gone and the same number of things to guess. And eventually we get down to the main program. We see that a Hangman game is something which starts in the running state with some guesses available and maybe some words, and it ends in the not running state. So somehow this program is going to have to get to a game that's either won or lost or abandoned. There's no other way out of this. We have to do one or the other. By the way, when I first wrote this, I gave it a slightly different type. I gave it this type, and so this is a slightly different precondition that says the word that we give it has to have at least one letter in it. And there was nowhere in the program that I bothered checking that the strings I was reading had one letter in it. And so the machine said, sorry, you can't have that. I thought that was actually quite lovely, because that's the kind of silly mistake I make all the time. And it's the sort of thing that you think, well, types can't help you with that. Well, I think they can. Another mistake I made is that given that the two things, number of letters and number of guesses, are numbers. So here we've got a guess. If it's true, then it prints a message. If it's false, then it prints a message. This really happened as well. I got the wrong variable, and because it changed the wrong bit of state, it told me it went wrong. But if you peer at this for a minute or so, you can see exactly what went wrong, and actually it should have been a guess. So I've got a list of words just to show that there's some type inference available. So I can't be bothered to give the list of this word. I'm just waiting patiently for someone to complain at me about this. There's a length of a string, and the machine will just say, okay, I'll work. You say to the machine, you work out the length of this list. Has anyone spotted the problem with this list of words?
Scala.
Yes, Scala isn't in it. Because that compiles and runs, we know we are going to get a fair game of Hangman. So it'd be quite amusing if it picked Scala now, wouldn't it? Sadly not. I don't know what that might be. I'm going to lose, aren't I? Oh, probably basic. Yay. Good. Right, so, just one final thing, because I think I'm out of time. I do want to show you my partial proof of Pac-Man completeness. I haven't evolved this at all since I first showed it a couple of years ago. You'll get an impression for the speed of the Idris system when I do this. not necessarily in a good way. So this is a program that uses the effects library to manage the state of a Space Invaders game. So where the aliens are, where the Scrody Starfield is, where the bombs are, all of that. The bottleneck here, by the way, is GCC. So I need to figure out how to fix that. And there we are. So we're blasting assignment signs out of the sky here. So whoops! Oh, nearly went there. Anyway, enough of that. So, why do we care? Safety is something that people always talk about with types. We care about safety. But there's so much more. We can write expressive APIs. We can write generic programs. We can use the types to help us get to the right program. That's what types are really for. And if you're interested in learning more, you can learn more. I even have a special secret code. If you want to know the special secret code, which is 39 Brady, by the way, then you can get a discount on this. So if you want to learn more, it's not ready yet. I mean, there's only 2 chapters written, but it will be in progress over the next year or so. And all of the ideas that I've just presented, you'll get in some more depth. Okay, I'll shut up now. Thank you very much.
Unfortunately, there's no more time for questions, but I want to thank everyone.